last one. I guess I was in the middle of just writing down some things that we will need from last time. So basically the goal for this talk was, so if you remember from the last two talks, I defined this notion called spectral independence. I showed you a couple techniques for establishing spectral independence, and then I stated some theorems that I never proved or even justified at all, which is that this property of the distribution actually says anything about mixing. Okay, so the goal of this talk is to give you some intuition behind that. Okay, okay, so maybe let's just recall just a few pieces of notation. So recall that so if I have a Markov chain, say global dynamics, then it has an associated quadratic form, for which I measure the local variation of a function. It's given by this formula. It's not so important what this is, and I'll actually rewrite this later on. But if you want something concrete, this is it. And then what we're really interested in terms of being able to control these mixing times is these functional inequalities. So I compare, say, the global variance of a function with respect to the local variances, or say the global entropy of a function with respect to the local entropies, and so on. Okay. And I guess I was in the middle of writing, so just recalling what is spectral independence. And again, for this talk, let's just work on the Boolean cube for convenience. So the spectral independence just says that the largest eigenvalue of a certain influence matrix or correlation conditional influence matrix or correlation matrix is upper bounded. And just to make sure we're all on the same page, just recall that the entries of this influence matrix, they are given by conditional influences. So now let me just recall what we saw yesterday regarding the connection to fast mixing. So we had the following two theorems. So the first theorem is essentially due to 11 now, although there were also precursors of this from the high dimensional expander community, which is that if mu and all conditionals are beta spectrally independent, then the spectral gap of the Glauber dynamics is lower bounded by 1 over n, the 1 plus eta. Okay, this was the first result, and the second result, something that will allow you to control something more fine grained. So you can get control on even entropy. So assume spectral independence, or really the same condition as above. And if I make two additional assumptions, then we can get a much better bound. So if I assume that it satisfies a global Markov property, respect to a bounded degree graph, G. And third is the slightly more technical assumption, but is necessary for something like a standard log Sobolev inequality, that all marginals, say, are constant order, even under conditioning. If I make these three assumptions, then actually I have like a log Sobolev constant for p nu, lower bounded by order 1 over n, and really get bounds for all of the functional inequalities I want. And in particular, I'll get n log n mixing. Okay, so my goal for this talk is to give you essentially a complete proof of this. Although, so I guess I should first say, if you recall from I think Irit's talk, she talked about the equivalence between two notions of high dimensional expansion. One which is based off something called local spectral expansion, which is, we saw yesterday, is equivalent to spectral independence. There's that notion of high dimensional expansion, and it's equivalent to something called random walk expansion. which is essentially mixing for these walks. So it turns out if you take that proof or that theorem and you sort of inductively apply it, you can prove this. But I guess my goal for this talk is, or one goal is to sort of show you like a more just purely probabilistic proof of this. Okay, and then it'll be useful to do it that way so that I can also at least give you some semblance of an idea of how you can do this one. Okay, prove a much more refined state. Okay, so so here I'm just assuming only spectral independence, but I can only deduce a bound on the gap. And the spectral independence goes in the exponent of n. Here, if I make the same assumption, but I also add 2 more assumptions, I get 1 over n. And I guess, of course, there's some dependence on the spectral independence, but it's not in the exponent of n, crucially. Yeah.
It gives us better dependency on this not term on the
That's right.
minimum probability. But in the third assumption, we assume that every marginal of theta 1. Does that say anything about the minimum probability?
This is exponentially small, but that you still want log to kill that, right?
So the minimum probability can still be.
Yeah, it's still exponentially small. Yeah. Other questions? Okay, so before we sort of invoke spectral independence, let's first ask ourselves how to do this for product measures. Okay, so I guess the cool kids will probably do Fourier analysis or even stochastic calculus, but I'll do something a bit more barehanded. So let's just do it for product measures. Is green okay, or is it too? So first thing, let me just say that, okay, so I keep using the word, this theoretically form is like a local variance. And there's actually really, I mean, if you look at this, you say, okay, it kind of looks like it. I'm comparing the variance across Philippian coordinate, but there is really a formal sense in which this is true. So I can rewrite this theoretically form as follows. Okay. So another way to rewrite this theoretically form, at least for Glauber dynamics, let's now just say hit it with the same function. This is really equal to. So I am taking an expectation. I can think of it as taking an expectation over a uniformly random coordinate, an expectation over an assignment of all vertices on all the other coordinates, sample from the appropriate marginal distribution of the variance after conditioning on everything except the ith coordinate of the function. Okay. So let me help you parse this to make sure we're on the same page here. So you should really think of this expectation over everybody except I. It's just coming from this summation here, where I'm taking an expectation over a whole configuration. And then this average over the choice of coordinate is really just the average choice of which coordinate I'm flipping in the dynamics. And then I guess the rest of it is just calculation. But this is sort of a formal sense in which you can see this really is a local variance. So it's a Okay, so really what Poincare means is that global variance approximately factorizes. This is bounded by, so this is, so Poincare is equivalent. The same thing as the global variance factorizes. Sometimes this is called factorization or tensorization variance, or like I say, an approximate version. Okay. Okay, so how do you do it for product measures? So really, it's just the following lemma, which is, I think it's like a very nice exercise in convexity. It's something very generic. It says that if basically for all measures mu and nu, and for all functions f, we look at the variance with respect to the product of mu and nu under f. This is at most. So I can take the expectation over a draw from mu, the variance under a draw of nu at tau sigma, and plus the same thing, but except now on the outside, I take a draw from nu. Variance with respect to a draw from mu, the same quantity. And also the same thing for entropy. And this is really crucial uses that they're independent of each other. Okay, so it's first off, is this notation okay? Is this notation clear? And also what this means? Or okay, so this is like a nice exercise in convexity. But basically, if you have this lemma, then you just inductively apply. If you have a product measure, right? All the corners are independent, so I'm just going to peel off one coordinate at a time. And what you'll get, so by induction for product measures, you'll get basically optimal constant there, which is, say variance mu is upper bounded by n times. And that's like the optimal constant. Okay, and it really is n. There's no extra hidden constants or anything. Okay, and let me just say very briefly, so this thing also holds for entropy. And if you have this sort of entropy factorization, let's say you have a slightly different constant, like rho entropy, the global entropy of a function is at most the expected local entropies. So I minus I. And this in a completely black box manner. So first, this implies another nice exercise in convexity, implies a modified Log-concave inequality. Most, at least rho. It also implies a standard Log-concave inequality with constant at least rho times essentially the constant depending on how bounded your marginals are. Okay. So what this really, yeah, this is a bit of a technical point, but I'm just saying that if I can establish something like entropy factorization or tensorization of entropy, I can also deduce these kinds of things. But I don't want to get into much details there. Okay. But questions on how to do product measures, because from here on, we're going to sort of try to generalize this to like approximate versions and then use spectral dependence. Just again? Huh? Right. Exactly. Yeah. That's like at least one really useful way. Okay. So now. So in this language, I want to first reformulate this theorem. So this theorem looks very spectral, very linear algebraic. I'm just going to reformulate it in terms of variance factorization. Okay, so that'll be also sort of suggest the proof or how we're going to prove it. Let me restate the 11 Lau theorem. So Lau restated. So okay, so I'm writing in terms of variance factorization. So I'm gonna have the global variance on the left-hand side. We have the local variances on the right-hand side. And I guess now it's a question of what constant to put here. So it's going to have the following form. It's going to have a product form because we're going to do induction, basically. But basically basically it's exactly this expression here. So I take a product from j from 0 up to n minus 2 of 1 minus 1 plus eta. If you approximate like exponentials, then you can see that it's really just this. Okay. Okay. Questions? Okay. So like the proof for, in some similar sense to the proof for product measures, we're going to do it by induction. Okay. So first I claim that it suffices prove, I guess I'll call this inequality star, which is really just sort of the one step. So you can think of it like here, I've not conditioned on anything. And here I've conditioned on n minus 1 many coordinates, right? So instead of going from 0 to n minus 1, it's going to condition on 1, condition on 2, condition on 3, and so on. So I just need to prove, so I claim that it suffices to prove the following inequality, that if I look at, okay, up to this factor of 1 minus 1 plus eta over n, the global variance factorizes slightly. Factorizes as, well, if I take expectation over the coordinate I, but now an expectation over only the assignment to only that one vertex. Okay. And I look at now just a slightly localized variance. I claim that this suffices. Why? Because then I can iterate this, apply the star inequality to each of the conditional measures, right? Because remember, I'm assuming that all conditional measures are spectrally independent, right? Is that okay? So in particular, so if I apply star like k times, I guess I'm writing this out because I'm going to need it later. If I apply this k times, then I get that, look at the product over j from 0 to k minus 1, 1 minus plus eta, n minus j, global variance. This is at most the expectation over a random subset of k coordinates, expectation over an assignment to those coordinates, or into the correct marginal distribution of the sort of localized variances. And then of course, the case k equals n minus 1 is the claim. Okay. Okay, so let's see. I'll at least like sort of sketch the proof of star. I think it's a bit more just more of a calculation, but I'll show you like at least intuitively why this is related to like correlation inequalities. Okay. What is the proof of star? Okay. So the first thing that you would do, if you're doing conditioning, right? I have a global variance, and I do conditioning is I would apply the law of global variance, so or law of total variance. So what it means is just if I decompose my measure as just like a mixture, like say expectation over I sigma I of the conditional measure. It's like I'm decomposing my measure, then for every function f, the global variance of that function can be decomposed as the variance of the expectation plus the expectation of the variance, right? So I have the expectation over I and sigma I, the variance and plus is usually the most annoying term, which is the variance with respect to a random choice of I and sigma I of now basically the expectation. And a similar identity holds for entropy and so on. I can look at this thing and compare it with what I want from star. When I rewrite star, it's really the same thing. It's equivalent to saying that basically this thing is exactly what I have on the right-hand side here. It's equivalent to saying that I look at this variance here, variance under random choice of coordinate I and an assignment to that coordinate. Expectation function with respect to the conditional measure is upper bounded by 1 plus eta over n times the global variance. I'm just going to pause here. I guess it's a bit more of a calculation, but I've really done nothing fancy. I guess at this point, I could just tell you that, okay, so this is already starting to look very much like spectral independence. You should think of this, 1 over n here as really just accounting for the fact that I've picked a random coordinate here. And this 1 plus eta, so if you think of, say, this is like roughly the L2 norm of the function f with respect to a suitable norm. So it's already starting to look somewhat similar to this, but it's not so clear how to interpret this quantity here. Okay, so if I'm a bit irresponsible, I would just say, exercise, it's a calculation and just be done with it. But let me just give you a little bit of intuition without having to write everything out myself. Okay, let me just reproduce it here. So I want variance from under a random coordinate I, a random assignment to that coordinate, expectation under the conditional measure of function f is at most 1 plus eta over n is the global variance, which I'm really thinking of this as like so now is where I'm going to start interpreting things linear algebraically, because I have to get an eigenvalue at some point, right? So what does this really mean? So one way to interpret what this means is, okay, so this thing here, this is really like, if I imagine f as being a 2 to the n dimensional vector, this is really an inner product. And this variance is kind of like I'm picking like a random one of these guys, these inner products, and squaring it, right? So this here on the right-hand side, so the left-hand side is really it's roughly equal to, if I pick a random coordinate I, a random assignment to sigma I of this inner product. So now I'm really viewing things as vectors, like big vectors. But I can of course rewrite this, by pulling it out, everything out. This is equal to F transpose of now a matrix, very big matrix. I'm just interpreting this variance as like a quadratic form. Okay, we have some matrix inside. Now, this is a very big matrix, but it's a low rank matrix because I only have like n or 2n many terms here. So I have like a rank n 2 to the n matrix. And it's also, I guess, PSD or whatever. So you can just use, now I can sort of compress this matrix down, right? Because really now it's like, I'm comparing it with the global L2 norm of F. So it's really just asking for like the norm of this matrix. That's really all we're asking for, right? So now you can just use the fact that, then just use like this basically now derivative fact that sort of the spectrum, let's say like AA transpose is equal to the spectrum A transpose A, maybe up to like the multiplicity of the 0 eigenvalue, but you only care about the norm anyways. So so then the matrix you would get instead, and now it's just really inner products, pairwise inner products between these vectors. And if you calculate everything out, you'll see that you get like a correlation out in the inner. This is just like some intuition of like how you would carry out the calculation, but I don't want to bore you with that. So here I've only pinned one variable. Take a random coordinate, I pin only that coordinate. And I still have n-1 free coordinates. And each of them has this measure. Okay. Other question? And sure. Yes. So there are versions of, say, like factorization of entropy where I can pick a random block, a subset of vertices, and there are analogs of that. And you can also deduce like mixing for those using spectral dependence. Okay, so really, like, yeah, if you believe me that now that these two things are really the same, they're the same, then we've proven star by induction. I have my theorem, and then we're done. Okay, this is like an alternative way. That's like sort of like there's no like, or I guess a little bit less linear algebra. And anyways, but average spectrum. So I mean, I guess, yeah, but I mean, there are examples where even like if you have bad spectral dependence for just like a very small number of things, it's still the Markov chain is very poorly mixing. Yeah, I'm really like I have to apply because I have to take an average over these things, right? So I need to put the worst case, like if I'm going to combine terms, right? So I really need like a worst case thing here. I mean, you can make it slightly average case, but not to like maybe not to the extent that you think you can.
Because you don't have control on the mirrors. This notion of the some bound on the averages. Some of them get smaller.
Right. Okay. Yeah. Okay. Yeah. So Nima has some really interesting work where you get some kind of averaging here, but it's not like an average choice of I don't know if I wrote it anywhere. Like it's not over an average choice of this one. I take a worst case choice of this, but I get to average the ordering in which I do this. Okay, so there's like a little bit of averaging, but I mean, I think he has some interesting applications of this, but I think I'll let him speak for that. Yeah, I just want to keep things simple, like just more questions. Okay, so now what I want to do, I want to give you some idea of how to do this. Okay, so I guess here's the question. Like, all right, here's really the question of like, how you would think about this, which is like, where in this analysis was lossy, or well, another way to put it is, so there's a reason I wrote down this inequality here, this general version of K. Like perhaps a more suggestive question is just for what values of K is this actually fine? Okay, so maybe say more precisely what I mean by this. So So really what I claim, somehow things are very good for like small j, right? Because I'm only losing like 1 minus a tiny little bit. Things are only getting really bad if like j is getting close to n, right? So here is the observation. Or let's say I assume k is like it's equal to theta n or some constant, which I get to pick. I have this thing. So then, so what I claim is that really we have so up to some constant, we have very good factorization of the global entropy with respect to a random subset of linear size. It's just because, this is, so if I'm really looking at from j all the way up to only say theta n thing, it's approximately say exponential if you calculate it all out, minus 1 plus theta times log of 1 over theta. So theta is a constant. If I choose theta to be a constant, then I get very good factorization. So really, things are very good at sort of the bottom. Okay. So a dynamical perspective on this, what this says is that if I run the following crazy dynamics, which is in each step, I pick a random subset of 1 minus theta n many vertices, so a huge number of vertices, and I resample all of them, then this really crazy random walk is going to mix in one step or a constant number of steps, as it should, intuitively. But even that's like, non-trivial. Okay, but that's what this says. Of course, here I still have some like global-ish looking variance, right? Because I still have order n many vertices remaining. And I don't want to keep using spectral independence to further decompose these variances. And so this is exactly how we're going to use these two extra assumptions are going to come in. So what you really hope for is that, so now imagine, let's say you're looking at really now like a graph type model, right? So for instance, maybe like matching as we saw earlier, or like independent sets or something. So what I've done here is I pick a random subset of vertices and I've assigned stuff to them. I've assigned plus minus 1 to them. Effectively, I've just deleted them from the graph. Right? So I have a big graph of n vertices, but I've killed tons and tons of vertices. A constant fraction number of vertices are killed. Okay. So in particular, if this graph is sparse, what I would expect to happen if I kill that many vertices is that this graph should shatter into a bunch of small pieces. And intuitively, it helps me factorize this variance much, much better than you would expect otherwise. Is that rough intuition? I mean, I'll say more clearly how exactly formalize this, but this is roughly where we're going to go. Okay. Any questions about the plan?
Wait, can you explain again why exercise one step?
Yeah, very good question. Yeah. Yeah. So let's forget the factorization thing for now. Okay. So first, you believe that if I apply this k times, I get this kind of inequality where I take a product up to k, and now I'm sampling a subset of k vertices, and okay. So what I'm saying is that if I take k to be order n, not exactly n, but theta of n, then the coefficient I get here, this you should think of this as being, say, the spectral gap of the corresponding dynamics.
Spectral gap, you mentioned like log.
Okay, sorry. Yeah, now okay, maybe not order one, but yeah, log, but just like very, very fast. Yeah, sorry, I was being very loosey-goosey about it, but just Unix very much like very, very fast. Yeah. Okay, so what do we want to do now? So we want to control basically these variants after I've conditioned on the values of linearly many vertices. And since everything is at expectation, it's kind of okay if the bounds hold like with high probability, basically. Okay, so that's roughly how it's going to go. So basically, this is the hope. High probability. The choice of the vertices S. This mu condition on the assignment on S. It's going to factorize the product. So maybe let's call it, say, mu of, so I'm still conditioning on everything in S, but now I'm looking at a smaller subset of vertices. Where each, let's say U1, UT, are the maximal connected components of the induced subgraph after I deleted those S vertices. So of course, I can always do this by the conditional independence assumption, because if these connected components, they're maximal, then, and they don't have, there are no edges between them, so there's no like influence between them. But what we really care about is not only that I can do this, but that I have many components, and all of these components are small. Okay. So such that, I guess we don't really care that there are many components, but we want all of these to be small, which necessarily means that there are many. But such that small. Okay. Just be a bit more explicit on like why this is good for us. Just recall that lemma I showed previously. I have the variance for like the product of measures factorizes perfect. I can just apply this to each of these components. And once I've gotten down, if it really is the case that, for instance, all of these components are constant order, right? Then I can just have a constant size graph, like it's going to mix in a constant time. There's nothing, there's nothing, nothing really left to do at that point. Right? That's really the hope. If I have small graphs, then it's kind of okay. And really, I just need to ensure that the graph shatters. And that's where I'm going to use the bounded degreeness.
As long as there's that many random restrictions, it simplifies.
Right. Yeah. I guess I'm not sure what you mean by early stopping. You're not early stopping the Markov chain, or you just mean? Oh yeah, you're stopping this early because at some point this becomes too lossy.
Yeah.
Right? Yeah. Mm-hmm. Yeah, or like say log n is fine, but yeah, order one ideally. Right? But everything is an expectation, so it'll be fine. So start more. I want to state the shattering lemma, which really uses the bound agreeness. So if the G has maximum degree, so it's constant, and S is uniformly random, vertices choose, say, theta n many vertices. Okay, so I'm going to kill off order n many vertices. And for every vertex, for every L, the probability that, okay, so SV here just going to be the size of the is the maximal connected component that contains V after I kill off those vertices. Okay, I'll write it more explicitly in a sec. So the probability that the size of the connected component containing V equal to L is at most, there's some constants, delta times 1 minus theta. So, and let me just say, this is maximal connected component then do subgraph after deleting S. So in particular, if I choose my, so if, again, I'm assuming the degree is bounded. So if I can choose theta here to be a constant, and now I have exponentially small probability that my component is large. So an expectation is of constant order with very high probability. It's of like log n order, let's say. Okay, so I'll come back to this in a moment. Let's just like very quickly. We want to see how to do this. You mean like the proof of this, or do you mean that? Yeah, sure. I was thinking like, should I just like write out like the doing all this business? I guess I don't have that much more material to cover anyways, so I guess I could just do whatever I want. Okay, good. Okay, so okay, I'll say okay, yeah. So where does property 3 come in? So I guess so. Turns out, okay, if you just want spectral gap order 1 over n, you don't need property 3. Okay. The property 3 is really just so that I can get control on entropy based off of like correlations, which is like for variance instead. And that's really it. So I don't need property 3 if I want 1 over n gap.
And for MSI,
For MSI, you also need it because I need to be able to say that, so remember the star inequality. So we want that 1 minus, I want to put entropy F at most, say, entropy. So this is ideally, so this, if you have variance here, this is exactly what you get from spectral independence. We want this for entropy, but in order to get that from spectral independence, you also have to use the marginal bound of this inequality. Because otherwise, so I guess it's also a question of like, if you change your assumptions, sure, like then it just kind of goes through, but then you need to establish a stronger thing. This is like a classical thing. You can always like convert spectral gap to entropy at like some loss depending on, like the minimum probability. Okay. So I guess. Yeah, so I guess that typically it's a more okay. I mean, those are typically more calculations, but it's like, I mean, typically one way you can bound it is like, okay, I have a vertex. If I assume it's bounded degree, right? So for any choice of setting outside the neighborhood, I can compute the margin of that vertex explicitly, and I just do an average. I can bound it. Yeah. Yes. So for something, so okay. So yesterday I talked about a couple techniques for establishing it. For something like it really is like model dependent. So for the easing model on a boundary graph, you want to use like decay of correlations. But yeah. Other question. I guess really okay. Yeah. So I guess if you guys already believe this, then there's nothing left, very little left for me to do. I mean, I can just very briefly sketch out like some of the like how you like sort of combine all these things together, but after that, I guess maybe I'll just open up the questions or give some time back to everyone. Okay, so I guess I should also mention this kind of shattering type lemma for sparse graphs is like it's a very useful thing. It's not just like marker chains. Like apparently people even in distributed algorithms use this thing. Maybe I should also put a citation. So I guess the version of it we used is due to Borg's case. Okay, so I guess I'll just do the, okay, so roughly outline of calculations. I'm going to start with, of course, my global variance. I'm going to use this thing right here. Say it's upper bounded by, say, a constant times the expectation of a random set of vertices of linear size. Now, everything's an expectation, so I'm going to do a shattering. So my shattering. Now, we have the same thing here. Expectation for S. More expectations. Okay, so expectation over. Y. And now I just use something like any Poincare you want. Like you can even have like a very lossy Poincare inequality here. And so long as sort of the probability of having a large set sort of is much smaller than like the bad bound you use for the Poincare inequality. And use. I'm not sure it's that valuable to keep doing this, but that's really it. Hopefully I've illustrated the rough idea or intuition. Yes, I'll open up to questions.
How do you verify?
Usually that's like kind of like baked into your distribution, right? I mean, it's like all of like the classical combinatorial models, or not all, but like many of them, like independent sets or something, or matchings. Clearly, if I have two disconnected graphs, like a matching here is not going to affect the matching here. So spanning tree does not work, but spanning tree is the special case where like the spectral dependence is so strong that I don't even need this. Yeah, but there's a kind of miraculous thing that if you have zero spectral independence, then actually the variance, you can get entropy bounds from the variance. I guess like yeah, there's like a very like a convexity kind of thing that happens. We have zero. That's to like improve it even further. But in terms of getting MLSI, all this is like you add like extra convexity stuff for the local entropy contraction.
Does this have like interpretation in HDX language? I feel like it's saying you can skip all the, if all links of level theta n has some good property, then you can avoid some factoring.
Yeah, basically, right? I mean, you can always phrase it in HDX language. Basically, it's like after I've taken a link of like say S, then the remaining complex is really like I don't know what the right, it's like direct product, like what's the, it's like product of, you know, it's, whatever notation people use for it, but like smaller complexes. I mean, you should think of it like now, like the local blocks will have like a bunch of complete bipartite structure connecting these smaller complexes. So it's like even better expanding.
And in this case, because of like the global Markov property, it's like a true product, right?
Yeah, it really is like these are really just completely independent of each other. Yeah, that's right.
You only know like on some level they have very good, those links have very good extension. Can you also like
Oh, you're saying like, okay, because this is like a product of measures, then maybe just the spectral impedance is like much better for that without appealing to, is that what you're?
Also, I feel like this is saying the for those things much better.
Right. So I guess the trouble is though, is because first off, again, this doesn't hold for all S, right? This is like for averages.
Most S.
Yeah, most S. The other issue here is that, okay, you could study like the spectral impedance of this thing, right? And maybe it's much better than the one you get normally, right? But you know, if your spectral impedance is even like 2, you're gonna get a bad bound, or like 3, you're gonna get n cubed already. So yeah. Yeah, somehow it doesn't. Oh, okay, sure. Yeah. So I guess I mean, I guess the real workhorse is just like a sort of like accounting lemma that says, you know, if I have a vertex, I count the number of subgraphs, induced subgraphs that are connected, and that would contain that vertex. Okay. So that's like really I guess, so this was proved using this, but okay, the real lemma there was like, so for all max degree G, for all V, for all vertices V, for all L, the number of connected components size L containing, or, sorry, connected induced subgraphs containing V, something like E times E delta to the L. Okay. And this is actually not super hard to prove. Basically, it's like, instead of counting connected components, which is a little bit challenging, I just connect trees. I count trees that contain V. And if I want to count trees, then in some sense, the worst case you can do is look at the infinite tree, because having cycles is only going to reduce your number of trees. Reducing number of edges is only going to reduce the number of trees. So the worst case, you even know the worst case here is the infinite tree, irregular tree. So. Yeah, that's also, yeah.
And then you explore all the neighbors, and the second number of neighbors aligned is less than 1, so we just die out.
Final questions?
Thanks.
Thanks, everyone.
Yes, the measure.